Okay, here is an interesting paper. We'll cover this topic not because we are trying to be an expert in this topic, but it's an interesting potential climate solution that also has co-benefits in terms of agriculture, food production, food security, etc. Removing atmospheric CO2 through mass scale up of crops with enhanced root systems. So mass scale up because you want to have substantial level of carbon capture through this method, and of course agriculture is already occurring globally anyways. The Intergovernmental Panel on Climate Change IPCC estimates that societies may need to remove 5 to 16 gigaton CO2 from the atmosphere annually to reach global net zero CO2 emissions within this century. Typically we say 2050 if we want to hit 1.5 degrees C by 2100. Yet there has been little analysis of how quickly carbon dioxide removal or CDR strategies could scale up to meet this expected need. We develop a new integrated modeling approach for assessing scalability that combines insights from the history of analogous technological revolutions with information about the efficacy and specific constraints of CDR strategies. I have discussed what integrated assessment models are elsewhere. They are basically socioeconomic models that uh, include climate in some simplified form, and then they look at the climate interactions, climate impacts, and climate solutions in terms of energy, agriculture, transportation, infrastructure, buildings, land use, and so on and so forth. We illustrate our approach with genetically enhanced crops that grow larger roots and in turn increase soil carbon. Unlike many CDR technologies whose deployment will be slowed by the need for novel and costly infrastructures, history suggests that crop innovations can scale rapidly in countries that admit them. So if you allow GMO to come in, you can scale it up very quickly. There's a lot of controversies with them anyways, but still they are everywhere now. Within 13 years of the first deployment, diffusion of enhanced crop yields could peak and remove zero point 0.9 to 1.2 gigaton CO2 per year, about 7 times larger than all CO2 offsets applied today to the global voluntary offsets market. So you don't want to think about carbon capture as an offset because you want to actually reduce emissions as well, but nonetheless idea can be compared to offsets which are already being traded. Upscaling depends on policy and politics as they affect the total land area on which carbon absorbing crops are allowed. Early scaling could allow crop engineering to play an outsized role in a portfolio of CDR strategies that overall scales to IPCC-like levels of carbon removal, even though carbon storage in soils is less permanent than geologic storage. Ideally, carbon capture and sequestration would mean you will put it away for time scales of thousands of years, so that it's basically permanently out of the system on human time scales. But when you do soil sequestration, the time scale is much shorter, maybe order, let's say 1500 years, depending on the perturbation levels and so on. So I'm going to be very brief, skip almost all of the text and then jump to figure 1 here. They have some details on what's been going on and what technologies are available and what their methodologies are. So this is the conceptual schematic of the modeling framework. Our model calculates impacts to the climate system due to substitution of carbon enhanced crops and has 3 components that represent A, innovation and diffusion of new crop cultivars into existing agricultural markets. So this is the technology model, technological change model, soil carbon absorption model, and then here you have the output. Development of new carbon enhanced crops, diffusion into the market in pioneering country that accepts it and allows it in, and then market diffusion in follower countries where if one country has success with it and begins to have an impact on the market or in terms of meeting its nationally determined contributions in terms of carbon drawdown and so on, there will be other countries who see it as a viable option for themselves. Soil carbon absorption model looks at annual planting of carbon enhanced crops, and then that goes into increasing making soil organic carbon, and then there are also changes to agricultural practices, which are, regenerative, conservative, no tillage, low tillage, etc., to also reduce the sinks of carbon from agricultural activities and enhance the reduce the sources and enhance the sinks. So all this leads to net CO2 removal from the atmosphere, and the scenario case will look at the CO2 emissions baseline, and the climate model then will take the atmospheric CO2 concentration and calculate global mean surface temperature. So they go end to end. They do show some impacts of this approach to CO2 concentrations and impacts on global surface temperatures, and you will see that the results are a bit modest, but the scalability is very attractive, and then they list the advantages of this method of crop engineering to sequester carbon versus other approaches in terms of speed and scalability and so on. Okay, so there is some text I have to read. The historical patterns of genetically modified crops can be used to inform how innovations in carbon enhanced crops might diffuse into service under the real world conditions where technology, politics, social attitudes and policy politics and policy interact in complex ways. Historical diffusion rates allow for estimation of several parameters such as delta T that fit logistical functions, so you can look up the methodology section, which in turn can inform the future adoption of new innovations. For example, we'll look at figure 2 now, where we will see how historical patterns of adoption of GM maize in pioneer and follower countries inform plausible futures of carbon enhanced maize cultivars, which is also in figure 2. For historical scale up of all GM crops, we will you can see the supplemental figure 3, and then for modeled scale up of all enhanced crops, you can see the supplemental figure 5. So here is figure 2. So you have rice, maize, wheat, other crops, sorghum, canola, cotton, beans, barley, soybeans, and so on. The scale and rates of scaling of innovations with genetically modified crops. So this is now rest of the world. So you are looking at crops and then geographical distributions. India, China, USA, Brazil, EU, Argentina, Canada, and rest of the world here, taking up almost 50%. So what are we looking at? Global agricultural land in percentage given to GM in yellow and non-GM in gray, and these are cultivars by crop, and global agricultural land in percentage given to GM and non-GM cultivations, again yellow and gray. In our analysis, the area under GM cultivation is the total addressable market, TAM, total addressable market. It means when you do this, where can you actually sell these crops, and where can you sell the idea to expand the adoption. So these are for TAM for carbon enhanced crops, total addressable markets for carbon enhanced crops. It's one thing to sell yield increasing crops, drought resilient crops, disease resilient crops, but if you are selling some carbon absorbing, carbon enhanced crops, will farmers buy it? How will it be incentivized by governments for farmers to take up these crops, and so on, right? Historical scale up for one set of GM innovations for maize in the five main GM maize accepting countries. You can look up supplemental figure for historical scale up of all 4 GM crops, that is soybeans, maize, cotton and canola in the 7 countries, i.e. US, Brazil, Argentina, Canada, Paraguay, India and China, that compose our analysis. India and China allow only cotton now, modeled scale up of carbon enhanced maize cultivars using logistics functions that fit the historical data for GM maize. So they are doing some transfer of information for modeling purposes, assuming once it's allowed in, it will diffuse similar to the cotton or maize, whatever has already made it in to the cropping system. So here are the market shares. So different countries: Canada, US, Brazil, Argentina, Paraguay. So you can see that some of these have already hit 100%, and here is the market share by what am I looking at here? The is modeled scale up of carbon enhanced maize cultivars using logistical functions. So I should have looked at the dates. This is historical data. This is projections of modeled carbon enhanced maize cultivars diffusing into these countries. Okay, so again, you can imagine by 2050 having very high penetration of market share in terms of market share for these carbon enhanced crops, and then you have to compute how much additional carbon will be sequestered for that, which happens here. So you're looking at CO2 sequestration in gigaton CO2 per year for change in agricultural practice only, versus smaller, deeper roots, deeper roots, bigger, shallower roots, and bigger, deeper roots. So bigger, deeper roots have the maximum, and then they will max in terms of the soil saturation of carbon or something like this, and then the additional sequestration will begin to drop off, but it is still significant in terms of fractions of gigaton CO2. We need gigaton scale carbon sequestration if we have to be realistic about that being part of the solution portfolio to keep the global warming targets of 1.5 or 2 degrees C by 2100. So here are the current crops. These are the smaller, deeper roots, and these are bigger and shallower roots, and these are bigger and deeper roots. So these are combinations of carbon enhanced crops that they are imagining. Okay, doesn't mean they exist. These are modeling exercises. There is some details that I'm skipping here in terms of what the details are about GMs for carbon enhanced crops. Scenario without enhanced crops, so no enhanced crop deployment, change in agriculture practices only, which are happening a lot. Scenarios with enhanced crops: smaller, deeper, bigger, shallower, bigger, deeper. So you can see the various scenarios and how the future of global CO2 emission drawdown is expected to happen. They do several scenarios of modeling as well. I'm just being a bit brief because you look at atmospheric concentrations and how you can bend the curve. You can think about basically bending the curve on emissions by using carbon enhanced crops to draw down CO2. This is 2025 to 2100. Even if you adopt them in 2050, you're going to have impacts, right? So let's read the captions to be more accurate. Climate benefits of net CO2 removal assuming CURE Pole and MODACT emission futures. So they are basically transferring IPCC scenarios into their model experiment. Global net CO2 emissions given background economy-wide emissions in two scenarios: CURE Pole, MODACT. I'm not saying what they are. You can read up the paper. For IPCC's illustrative pathways IP that we also used somewhere. Yeah, here. IP scenarios is illustrative pathways of IPCC, and B is atmospheric CO2 concentration here. So it is atmospheric concentration, ppm. C is global temperature change relative to pre-industrial levels. So you are trying to again duck under 1.5 or 2. So what is the contribution from the two scenarios to the carbon drawdown and temperature mitigation? Okay, the result for the post 2050 period, when the climate effects of enhanced crops are more salient, so they become more important in the latter period. Solid lines denote median and so on. So obviously, if you start adopting along the way, when enough carbon has been drawn down and put into soils, is going to show up a couple of decades later. So that is called the post 2050 scenario. Okay, the two scenarios are explained in the paper, but I don't want to go into details because my main goal is to show you that these ideas exist, that we have to produce food. So agriculture now emits about 25% of the total emissions, and then there is emissions from food waste as well, and people are trying to reduce both. And then there is the idea of increasing crop yields, grain production, etc., by using GMs, also making them drought resilient, pest resilient, and climate resilient overall, and so on. And then there is the idea of using crops themselves to take up more carbon with these carbon enhanced crop ideas. Okay, what are the implications for atmospheric concentration of CO2 and climate? We investigate the effects of enhanced crops on atmospheric CO2 removals and the climate. Calculations of climatic impacts require projections of future global emissions. We use two widely discussed scenarios from the IPCC's recent sixth assessment, CMIP 6, that explore the consequences of current policies and pledges, but in which further ambitions fall short in terms of meeting the global warming target. A world where CDR has high value to compensate and where a world where CDR has high value to compensate for failure to cut emissions. Okay, so I've cut out a lot of the text here and just reading the most salient points. Despite these modest reductions in atmospheric CO2 concentrations and in temperature, the deployment of carbon enhanced crops is only one of several CDR pathways that are possible, one of many actions that can in fact be taken together. So CDR itself is a part of the overall portfolio of solutions, and within CDR portfolio you have many approaches, as we just saw in the previous podcast. Direct capture from the air, pump it into the ocean, pump it into land, and crops, enhanced carbon crops of course are a way to pump soil, carbon into soil, so that's also a land-based approach. Okay, so this carbon enhanced crops themselves will be a part of the portfolio of land carbon sequestration. What are the critical uncertainties in terms of policy and technology? Uncertainty will be pervasive in any assessment of a nascent technology. For the scaling and plant soil components of our model, we identified 8 uncertain parameters and analyzed each across their possible variations to quantify the full range of the unknown. Okay, I won't go into the details there. From that full assessment that came out of this IPCC, 5 political and technological variables emerge as most important. I will look at the figure. The political variables are much greater in total uncertainty and importance. So, technology variables, total root mass, deep root mass, political variables, TAM that we talked about, which I already forgot. I hate myself for that, but sorry, I'm getting old. La la la. We already said what TAM is somewhere. Technology, adaptation. No, let me not guess random things. Right? Where were we? TAM is total addressable market. Total addressable market for adoption of this technology. Okay, so for the full assessment, 5 political and technological variables emerge as the most important. The political variables are much greater in total uncertainty and importance. So here we are, technology variables, total addressable markets here, huge, plus 169.5%, and there is also area involved, other variables involved, carbon per hectare, tons of carbon per hectare, delay in adoption in follower countries could be 6 years on average, but 16 to 0 is the range. Delay in adoption since first regulatory approval. So even if it is allowed, then how long will it take? Maybe 3 years with a range of 10 to 1 years. Change in carbon removals, decrease and increase. What does it mean? Cumulative net CO2 removal sensitivity to plausible variation in political and technological parameters to total root mass and deep root mass by 2050 and 2100. And so that's from total root mass, deep root mass, and TAM is only positive, so increase the change in carbon removal. Delay in adoption actually can decrease carbon uptake, and delay in adoption since first regulatory approval or smaller but still can impact carbon removal. Okay, so you want total addressable markets to be captured fully, not just the potential to achieve maximum increase in carbon removals. So this is net cumulative CO2 removal through 2100 by country for two scenarios that differ in the crops that are enhanced and countries that accept them. A baseline scenario in which today's 4 main GM crops, namely soybeans, maize, cotton, canola, are carbon enhanced and accepted by the 7 main GM accepting countries that we mentioned before. And B is the scenario with broader development of carbon enhanced cultivars that include wheat and rice, which dominate the agricultural production and markets, in addition to today's 4 main GM crops we talked about here. Alongside wider acceptance by China, India and the EU. So you can play these scenarios in many ways, that you have the same crops, more countries, or more crops and more countries, and so on. You're basically looking for the potential for sequestering carbon into soils using these cultivars, which have root systems that can take up more carbon, right? So let's read the conclusions. I may have another, no I don't. Modeling future changes in technology and their impacts is particularly challenging, as with most CDR systems, when there is little theory and no evidence of how scale-up will occur under real-world conditions. The central contribution of this paper is to help address this challenge by offering a framework for assessing scalability and illustrating it with a novel CDR approach that involves enhancing crop root systems to replenish carbon in soils. Our framework combines theories of technological change with insights gleaned from comparable historical experiences that can reveal how producer interests, public acceptance and other analogous real-world factors may shape adoption of novel technologies under real-world conditions. With CDR technologies in particular, existing integrated climate system models reviewed by the IPCC have struggled to reflect those kinds of real-world factors. There are a lot of issues with IAMs or integrated assessment models, but in this context, real-world factors are not as effectively captured in IAMs as one would like. 3 observations about enhanced crop CDR stand out. First, in comparison to other CDR methods, CO2 removals from crops engineered to grow larger root systems could accrue rapidly, probably much more rapidly than all other major CDR options for direct air capture, land and ocean, okay, like growing forest. Can take years and years. Second, any analysis of an immature technology scaling into the unknown hinges on many assumptions. Sorry, I stressed this wrong. Second, any analysis of an immature technology scaling into the unknown, I need a comma here, hinges on many assumptions, any assumptions whose proper values are unknowable ex ante. Our assessment suggests that the most important uncertainties are political factors that affect total addressable markets for carbon enhanced crops, which we looked at a little bit so I skipped there the text. Third, we have not addressed in this paper a topic of importance in other studies, the apparatus for monitoring, reporting, and verifying CO2 removals. Every time you say you have used something to remove carbon, you have to show that you have removed more carbon than would happen anyway. If you're doing agriculture and you're saying that sequestering some carbon, then carbon enhanced crops have to be shown that they are sequestering more carbon into the soils than normal plants, normal crops. Okay, that's monitoring, reporting, and verification. The MRV regime for each CDR method requires knowledge of how the overall systems affect net carbon removal, so that MRV can focus on those attributes most germane to the performance. So that basically says that they claim that they can help elucidate those attributes and also identify trade-offs that could affect MRV design. So they are saying their model study also helps with monitoring, reporting, and verification of CDR, not only for their method, for other methods as well. Okay, well, it's a nice idea. I don't know how far we are from actually having crops with enhanced root systems that can sequester more carbon, but I'm sure companies are working on it, researchers are working on it, because again, there is money to be made, so we'll wait and see when it may come into practice in the real world. Okay, let's leave it here.